Alrighty, welcome back to 353. So this will be our last hardest topic, so that'll be fun. So think everything. This is not on test 1. So again, test 1 goes up to lecture 1, or sorry, of course it goes up to lecture 1. It goes all the way from 1 to 8. Jeez, I'm off my game today. So lectures 9 and 10 were kind of review-ish. We kind of applied some topics, so I won't test you on MMAP or anything like that. But some of the things may or may not help you. So it's already written. Also, just in case you didn't see the announcement, it is in the exam center, and it is at 9, everyone's favorite time. So starts at 9:10 exactly, and then goes to 9:55, so you have a hope of crossing the street and making it to your next class or whatever you shall do. But yes, I'm sorry you have to get up at some ungodly hour, maybe if you commute in. I know I will be waking up at 4 a.m., so yay. All right, so threads. So first, we get a fun, silly, real-life example because we have to talk about concurrency and parallelism. So for most people, for most normal people that aren't computer scientists, those two words are synonyms, or whatever the English word that is. I don't know. I failed grade 10 English. Well, not really, but I got really close. But computer scientists are weird people, and concurrency and parallelism do not mean the same thing. So the difference between the two is concurrency means I'm switching between two or more things. It means I can get interrupted and make progress on, well, I can only make progress on one thing at a time, but I can switch between the things I'm making progress on. So the goal there is to make progress on multiple things. While parallelism, two things need to be happening at the exact same time instant. So it means they're independent, they mean they are happening at the same time. And that goal is to run as fast as possible. So again, I have multiple cores, 2 in my watch. Every system nowadays you'll want to exploit some parallelism. But back in the day, you know, concurrency is also important too, especially if you are doing stuff like web server stuff, loves concurrency. So let's have a silly real-life situation to explain the difference between concurrency and parallelism, because one does not imply the other. You can have something that is, well, concurrency and parallelism is typically between two things. Between two things, they could be able to be done concurrently, or parallelism, or any combination of that. So you have to bear with me for a second here, because we're going to have a silly real-life situation where we assume we are not animals and have manners. So you're sitting at a table for dinner, and you can eat, drink, talk, gesture with your hands. And there's this weird caveat that you're so hungry that if you start eating, you won't stop until you finish. So between two tasks, we can try and find ones that cannot be done concurrently and cannot be done in parallel. So for example, if I am considering the task eating, well, let's actually go with a different one. If I consider the task drinking and talking, can I do those concurrently? So can I talk, stop talking, pick up my drink, drink? Yeah, I should be able to do those concurrently, right? If I'm not an animal, can I do those in parallel? That means I'm talking and drinking at the exact same time. Some of you may be able to do this, but again, you have to bear with me here. We're trying to be civilized, so we would say we could not do those two tasks in parallel. All right, so what about, I don't know, eating and drinking? Can I do those two tasks in parallel? Again, not savages. So I can't do those in parallel, again, assuming I only have one mouth, right? Can I do eating and drinking concurrently? Well, in this case, no, because I have this kind of silly condition where if I start eating, I can't switch. So concurrency is being able to switch, but here Well, I can't switch between eating and drinking because if I start eating, I'm not going to stop. So I can't stop halfway through eating. Again, this situation is kind of rare in computing and rare in real-life examples. So again, slightly contrived, but that's just to show that they do not imply each other. What about eating and gesturing? Can I do those in parallel? Yeah, I have another free hand, so I can eat and gesture. But I can't do those concurrently because I can't stop eating to just solely gesture. So again, I have the weird situation where, again, one doesn't imply the other. And then for the rest of them, gesturing and talking, well, between these two, I could do them in parallel or concurrently. It doesn't matter. I could stop, I could switch between them, I could do both at the same time, and same between gesturing and drinking. So I could do those, again, both concurrently and both parallel. So through this silly example, everyone get the difference between concurrency and parallelism. And the reason why it is kind of hard to tell which is which, so here's all the real-life examples. So the reason why it's kind of hard to tell with computers which is which is because if you do concurrency really, 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 really quickly, then it will kind of look like parallelism. So, you know, again, silly example, if I have a blue drink and a red drink in front of me, and I tell you to close your eyes for 60 seconds, and then you open your eyes and they're gone. You don't know what I did. I could have done them concurrently or in parallel, right? So if your time scale is much, much, much larger than me actually switching between things, they kind of look the same from your perspective. So that's often what happens with computers, especially if we had a single core back in the day. Looks like we can do multiple things, but really computers just switch really, really quickly. And again, with that silly real-life example, you don't know if I just downed them both at the same time, if I'd like double-fisted them, or if I was switching, or what I was doing, right? All right, everyone on the same page with that. All right, let's start talking about threads. So we all like processes. It was everyone's favorite thing. So we do threads, which is like processes, but with shared memory, which is even worse. So they're the same principle as processes. They enable some parallelism to happen, except by default, they share memory. So when you create a new process, it's completely independent from the original, right? A whole new virtual address space. One doesn't affect the other. In the case of threads, they are not completely independent. Threads have the same address space. The only thing independent in a thread is its current registers, its program counter, which is also a register, and its stack. So in your intro course, or one of your intro courses, or the other kind of architecture course, they harped on to you about like stack versus heap and things like that, right? So now it is going to matter because if I use the stack, well, if I use the stack with threads, it's independent. While if I use something like the heap, it is not independent because it's all sharing virtual memory space. So they have the same address space. So if I change something in one thread that isn't on the stack, it will appear on the other thread. If I want to have non-stack memory specific to a thread, I can do something called thread local storage, or TLS. Again, TLS also means some other things for security. It's an overloaded term, but we won't go into specifically how we do that. Just know that it is an option, and some things are actually stored in TLS that we have been using, like that error no thing. So the rule between process, or the relationship between processes and threads are one process can have multiple threads. So by default, a process just executes code in its address space. Technically, the easiest way to think about it is that initially a process just has a single thread that starts executing main. But because I can have multiple threads now, I'll show you how to create them in a little bit, we can have multiple executions in the same address space. So multiple kind of virtual processors going on, which may be actual different physical processors. Again, depending on my machine, whatever my kernel decides to do with scheduling them, because the kernel will schedule them exactly like we've argued about before with all of our scheduling algorithms. So the idea behind them is that they're lighter weight. They only need a stack and a set of virtual registers. So they're less expensive to create than a process. They share code, data, basically everything in the same address space, file descriptors, and everything like that. It's not that much that is independent for them, which is great if you had a lot of communication between processes. Well, if you had to use something like pipes or something, they have to go through system calls. It's slow. If you're sharing a lot of data, then, well, it's easier if they're in the same if they're in the same address space because everything's shared by default, so there's pretty much no communication overhead. I don't have to do system calls or anything like that. So, assuming I have one CPU, again, threads can express concurrency at minimum, but usually we want them to express parallelism as well. So one process can appear like it's executing multiple locations at once. However, this could be just an illusion. The OS context switches within a process, and it could be going really, really fast. Even if you have a single CPU core, or you're using Node or something like that, some JavaScript framework, it's all single-threaded, and it heavily relies on concurrency. So, for example, web servers typically look like this. There's a main part, like in your main thread or in your main function. It'll be something like this. So like while true, I get a request. So that'll be from something that looks like a file descriptor. I'll show you it in a later lecture just in case you're interested. But I accept a request. Essentially, I get like a new file descriptor that represents that request. And then I might just create a thread to process that request. It would be using your network card, which is I/O, which is typically slow. So it can juggle many, many connections all at once and make them appear like they're all happening at the same time, even though it's just juggling between them really, really fast because your CPU is a lot faster than network connections. But those two lines are basically a web server. So if you've gone to google.com or anything like that, that's basically what it looks like. So in summary, they're lighter weight than a process. So a process has an independent code, data, and heap. With a thread, they share code, data, and heap. Processes have independent execution. Or again, you can think of a process as just initially just having a single thread in it. While a thread must live within an executing process, and we'll be able to relate them between processes pretty much one-to-one, except for that parent-child relationship. So processes has its own stack and registers. Thread has its own stack and registers. For a process, it's more expensive to create and context switch them because, well, as you're learning from Lab 3, hopefully, you'd have to create a new virtual address space. You have to create a whole new set of page tables. You'd have to create a whole new set of file descriptor tables, everything like that. So obviously, it's going to be more expensive to create. While threads, all you have to do is create a stack and a set of virtual registers. And context switching is cheaper and faster because if I'm context switching between threads within a process, I don't have to do that thing where I flush the TLB or anything like that because it's all the same virtual address space. Everything is still all valid. While if I'm context switching between different processes, I'd have to flush the TLB as we went over before, which is much slower. For processes, they're completely removed from the OS when they're exited and waited on. And for a thread, whenever they're waited on or cleaned up, just its stack is removed from that process whenever they exit and get cleaned up. And then the only caveat here that's slightly stranger is that when a process dies, all the threads die within it as well because threads only exist within a process. So throughout this course, we'll be using POSIX threads. Pretty much everything is built on these. For Windows, of course, there's a Win32 thread, but we're going to use Unix threads. You can actually use this on Windows too. A lot of people do because, I don't know, they just like it better. So how you use it is you just do #include pthread.h in your source file. There's short for pthread, short for POSIX threads. and then you just use this -pthread for compile and linking the library. For all the code I give you, I've already done this for you as part of the build system, so you don't have to worry about it. So all the pthread functions have documentation in the man pages, and we'll be going over them as well. So for creating a process, we used fork. Well, for creating threads, all of our functions are going to begin with pthread underscore, and they're going to be named slightly better. So instead of fork, there is pthread create to create a thread. So it has 4 arguments, which is a bit more fun. So it needs, as the first argument, a handle to a thread at a pointer location, which basically means you create a pthread underscore t, which is basically an int, kind of like a process ID, but just for a thread. And then you give it the address of it, so it can go ahead and set that value as part of creating. Then it takes a pointer to this attribute function. We won't be using it. We'll just be using it null to get the defaults, and we'll see more details on things you could do, but won't be relevant for this course, but you might find it useful. Then the next is a start routine. That's the function to start execution. So looking at the type of this, void star start routine void star. Anyone want to tell me in plain English what the hell that type means? Everyone remember their pointers and C horribleness? Yeah.
It's a pointer to a function that can turn any pointer and takes them any pointer.
Yeah. So what this is a pointer to a function. And that function takes a single argument, which is a pointer. So void star is just C's way of saying it's a pointer to what? I don't care. So it's a pointer to something as its argument, and it returns a pointer. So if I want to actually give it, like set this to a value, that's what I do to this int arg. So this arg is the value that gets passed to that start routine function. So whenever the thread is created, it's set up that it runs that function, and the initial value of the argument is given by that 4th argument here. And here, pthread create will return 0 if it's successful. Otherwise, it directly returns an error no instead of setting that global error no variable. And if it returns an error, the contents of dereferencing that thread are undefined. So let's see how we use it. So this will be fun. All right, so this is how we can use it. So again, our execution would start in main. I create a pthread thread. Then I can do pthread create. I give it the address of thread, so it can go ahead and set it. Set the attributes to null, so I want all the defaults. Start routine is the address of run, and run is this function here that I just put this weird attribute so that the compiler wouldn't complain at me, because this argument I do not use at all in this function, so that's what this does. It's just to use to shut my compiler up. So I have the right function signature. I take a void pointer, and I return a void pointer. So in this run function, I print off in run, and then I return null because I don't really care. And then in here, the initial value I give to arg is null because, again, I don't use it. And then I print off in main. All right. So if I run this program, what should I see? Any guesses? Yeah?
You should print off in run and in main.
Yeah, so one thing I could do is print off in run and in main. So if we thought of this pthread create as a process, the only difference is it kind of works in the virtual address space, but it basically just creates another process that runs this run function, although memory is shared. And when it is picked to execute, it will just run this in run line and print this. And then the parent process, again, if this was processing and that was fork instead of create, the parent would just print in main. And then whenever I run this, I should see in run and then in main. In that order? Has anyone used threads before? Okay, so some people have, and some people's experience is, yeah, just use threads. It'll make things a lot faster, and that is horrible advice because you do not know the first thing about threads. So our first thing about threads is it would be a good guess to assume this prints in run and then in main, right? So let's go ahead, give it the old setup. Whoops. Give it the old setup, give it the old compile, and then this is called pthread example. Oh, I'm trying to CD. Of course I shouldn't CD. I should just run it. So if I run this, I get in main, in run. OK, cool. I run it. I get in main. Uh-oh. I run it. I get in main. I run it. I get in main. I run it. 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 Hey, I got the other one. I got in main and then run. So this is very not consistent. Anyone guess why this is happening? Why did I only see in main? Yeah.
Because if main finishes running and it exits and it kills the other thread before it does anything?
Yeah, so basically, after I have pthread create, I have two threads in this process. One would continue on and print in main. The other would start, if it's picked to run, will immediately print in run. So again, this is up to the scheduler, just like for processes. I don't know which one will run. So in a lot of the cases when I ran it, the main thread, that's what you call the thread that originally runs main, just prints off in main, and then we return 0. So remember, return 0 from main, whoops, is the exact same thing as like exit 0. So it means this process is now donezo, and all threads live within the process, which means the thread that was set up to execute in run gets murdered. So it gets murdered, it's no more. So that is why I always see in main no matter what happens. All right, questions about that before we fix stuff? Yeah? Yep, so did we see in run first and then main? Yeah, so it's technically possible that we see in run and then in main and then it exits. Probably, it's slightly unlikely, but it is possible. But most of the time, we'll see in main, then nothing, or in main, then in run. Again, we have no idea. So if this was a process, what am I missing in my process if I was to be a good parent? Yeah. Yeah, I could wait for it, right? I could make sure I can clean up my child and read its return value and everything like that. So what I could do is there's a wait equivalent for threads. So you can acknowledge your thread, and how you do that is, annoyingly, it's not called wait, it is called join. So the function for that, again, is called, everything is prefixed with pthread underscore, so this one's called pthread underscore join. It takes that pthread t, which is basically the thread ID set by the create, and then we get this. So void star star, everyone loves that. So the return value is void star star because, well, there's like some equivalent between processes and threads. So when a process exits, what we really care about is that it sets its return or its exit status, which is an integer, right? And because of that, whenever we use wait, we give it a pointer to an int so it can go ahead and set its value. So the only difference here is processes by default, you can think of them as returning an int. Threads by default just return a pointer. So if I want to get the value of the pointer, I have to give it the address of some pointer variable so it can go ahead and set the actual address there. So that's why it's void star star. So this would be set to the return value of the run function. So whatever that run function actually returned, that would be its kind of equivalent of an exit status. So stores the exit status, or basically the return value of the thread, set by pthread_exit. So we haven't gone into that. Whoops. So we haven't gone into pthread_exit yet, but there's an equivalent exit for pthreads called pthread_exit, which instead of giving it an int, we just give it a pointer value, and that goes ahead and just sets that value for us. If it's canceled, so there's a way to kill threads. So like we can kill processes, we can kill threads. It's called canceling them. So if they're canceled, it gives you this return value of pthread cancel. And if you just want to ignore it, you can set that pointer equal to null. And unlike wait, where if you wait on something, well, it's cleaned up, everything's done, the kernel knows about it, and would give you an error if you waited on it again. For pthreads, because they all exist in the same address space, you can call this multiple times with the same number, but it is technically undefined behavior. So you should only call this one time per thread, and you have to ensure that. So that is one difference just because they're in the same address space. So if I want to change my code so that I always see both lines, well, if I want them to happen in any order, then in the main thread, I should wait for my, there's no equivalent of a child thread, but wait for the other thread to end. So here I would do pthread join. I would join on thread, and I don't care about its return value, so I could do something like that. So if I join it, now I will always see in run and in main. But in this case, if I join it after I create it, I still have no idea what order they're going to be in. Likely, I'm going to get the exact same order every time, but it just happens by chance. So this time when I run it, I will always see in run and in main because I'm waiting for it. And I just happen to be getting lucky such that I see in main every single time I do this. Will I get lucky? I should probably give up around now, huh? Whoops. All right. OK, we didn't see a miracle. So it can happen the other way. It's just highly, 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 highly unlikely. All right. Any questions about that? And this also nicely cleans up that other thread, right? So now I'm nice. Yes?
Does like exit thread implicitly get called by the run function?
Yeah, so that's a good observation. So in the run function, just like the main function, if it makes it to the end, this is essentially the exact same thing as pthread_exit, and then that value just gets returned there. So it's the same idea. Pthread_exit just takes a pointer value instead of an int, and it's implicitly called if it makes it to the end of this. Just like if a process makes it to the end of main, it's implicitly called at the end. So exactly the same thing. If I want exit early, I could do something like pthread_exit. If I give it a value I don't care about, I could do something like that. And if I compile and run this, I'll just never see in run because it will immediately exit, even if I join it. Well, and then I'll join it, I'll clean it up, and everything will be great. So if I go ahead and run this, I just see in main because the other thread just exited before it printed anything. All right, any other questions or anything before we go over more stuff? So threads are fun. Let's doot. So yeah, preempted me. So ending a thread early, again, you can do it using pthread_exit. Again, think of exit, just the only difference being instead of returning an int, you're returning a pointer. So that's why it's a void star. Return value, again, it's just C's way of saying it's a pointer to what? I don't care, you should know. Because of course it is at C. So that start routine, returning, again, is the equivalent of calling pthread_exit. So basically the exact same equivalent as returning from main, just calling exit. Returning from that start routine is the same as calling pthread_exit. So it'll be implicitly called at the end. All right, so what we saw is the default where they are called joinable threads. So for joinable threads, we have to wait for someone to call pthread join to release all of their resources. So unlike processes, I can just say, hey, screw that. I just want them to just combust whenever they exit. I don't care about the return value. They can just go ahead and clean themselves up. So one thing we can do is create something that does not have an equivalent in processes called detached threads. And with a detached thread, they release all their resources when they terminate. So the catch here is that if they release all their resources when they terminate, then I cannot read their return value because they're already gone, they're poof, they don't exist anymore. So you only prefer this if you do not care about their return value and you just don't want to bother waiting for them. You want them just to, again, release all their resources. You don't want to have them being zombie threads or anything like that. So in this case, the thread, that just marks the thread that's detached. And again, it returns 0 on success, error number otherwise. So there's also this caveat is if you call pthread detach on a thread that's already detached, boom, more undefined behavior. So that is a fun thing to look out for. Whoops. So, So if I wanted to, I could change it to use detach instead. So after pthread create, I can do pthread detach. So in this case, I didn't really care about its return value, right? So if I detach, now that thread's a detached thread, and it should clean up its resources whenever it's done printing in main. So now I have a bit of a dilemma, so now I can't join it, right? So if it's a detached thread, I can't join it, so I have to do something like this. So if I have this and I run it, will I see both lines again? Or will I see only one line sometimes? Anyone thinks we'll get 2 lines every single time using the detach one? No? OK. And most people probably think we might see 1 line and might see 2. It kind of depends. It's exactly what we had before, right? Where we don't know what's going to execute first. And, well, the main thread could execute first, print in main, exits the process. The other thread is now dead. So if I do this, compile it, run it, I'll get exactly what we get before. I see in main that time, in main, in main, in main. Most of the time I probably see in main. I might get lucky where I see 2 things. OK, apparently I only got lucky before. So no reason why I can't see 2 things again. It is highly unlikely. So your question might be like, hey, I don't care about its return value, but I still want to wait for it to be done. So in that case, if you only want to exit your process when all threads are done, basically what I want to do is avoid this. So the main thread will eventually return from main and call exit, which will terminate my process. What you are totally allowed to do with pthreads is I can just pthread exit from that main thread. So if instead of returning 0 from main, which would call exit, I can call pthread exit here. So if I call pthread exit, the way pthread exit works is it will just terminate that thread. So it will just terminate the thread that was running, that was initially created, that was running the main function. And if it exits, then what the rule is your process will still stay alive as long as there is 1 thread still remaining. So in this case, if the main thread prints in main and calls pthread exit, well, in the case that the other one hasn't run, it would kill the main thread, it would terminate, and then, well, the process wouldn't end. It would only end when when pthread exit gets called, and there's no other threads to execute. So the other thread would eventually get picked by the kernel to run, print in main, and then do its pthread exit. At the time it does its pthread exit, it is the last thread, so the pthread library is going ahead and terminate that process and call exit on it. So if I run this now, I should always get in main and in run, no matter what. Again, the order is unspecified. I'm trying my luck. It's not working. But again, the order is unspecified. I could see in run and then in main. Just so happens that likely, again, because of the way, well, we can kind of argue about it now. It's because of the way the scheduler works. So if I create another thread, well, the main thread's already running. It probably has some more time left. It probably has some more time slice left. So it'll just continue running, and printing main doesn't take that many cycles. So it'll probably just, in the rest of its time slice, just print in main before the other one even gets picked to run. So that's why it's likely it does that. But again, someone could come along and make their own scheduler that just prefers the new process immediately. And in that case, we would see the reverse order, again, depending on the scheduler. So any questions about that? Yep. Yeah, so the pthread exit there, pthread exit always terminates the calling thread. So in this case, the easiest way to think about it is initially your process is set up with a single thread, and that single thread is special, called the main thread, and it's executing the main function. So if you don't call pthread exit, it'll just do the normal C thing, call exit. But if you call pthread exit, then it'll terminate that main thread. Yeah.
So for threads, there's no like hierarchy, like parent or child about processing. There's no difference between a thread that creates another thread and a regular thread.
Yeah. So the equivalence between threads and processes basically stops at parent-childhood relationship. So with threads, there's no parent-childhood relationship because they all exist within a process, and that's it. So when you create threads, you don't have to wait on your child or anything like that because they're all in the same address space. Any thread can wait on any other thread. It doesn't matter. But there is kind of the concept of zombie threads. So if I have a joinable thread and it terminates and I don't join it, it's kind of it's like a zombie thread. So it still has some resources around. Your kernel can't clean them all up just yet. It has to wait for something to join to it. So it at least needs to keep its thread ID around. But there's no equivalent of like orphan threads because there's no parent-child relationship. So is a zombie thread the concept of a zombie thread, not an orphan thread? Yeah?
So when pthread exit gets called, does like return 0 get run as well?
So if pthread exit gets called here, then that main thread is just done. The main thread terminates, and it will never make it here. So it just ends. Yep?
You said earlier that shell calls forth to then run the main function.
Yep.
Is there a reason why we don't use threads within shell? Is it because of the virtual address space?
Yeah, so the question is, when I created kind of a new process, why don't I just create it in a thread? So for that, if I created in a thread, if my shell just created in a thread, then it would share the address with the shell, and it could probably mess it up, which is probably not good. So a lot of the times, if you don't want things to communicate, you definitely want them as a process because then they're independent, and if it crashes, it won't crash the other thing. So like here, if either thread crashed my program by doing a dereference or something like that, it would crash that whole process and bring the other thread that had nothing to do with it down with it. So like things like your web browser, your tabs will actually be implemented as separate processes and not threads because if a tab crashes, you don't want to bring down the entire browser, for example. So that's another reason, always kind of a trade-off for web browsers. They started off being threads and then they moved tabs to be in different processes instead. But again, always kind of a trade-off. But yeah, that was a good question. Anything else? Is that a question or? Okay. So, other things. Just so we can see how to use attributes. Again, we don't really care about them that much, but we can see how to get and set attributes. So there's this attribute called stack size. So how to use attributes is I have to create this pthread attribute type. Again, I can give it a lame name like attributes, and then you have to initialize it. So you have to give this attribute init function, the address of it, so it can go ahead and initialize that value, just like scanf or any other thing in C. And then if I want, I can do this get stack size of that attributes, so I can see what the default stack size is. So I give it the address of the attributes, and then the address of the stack size, which is the size t, which will go ahead and tell me what the default stack size is, so just to show you that there is indeed a set limit. So here I can print the stack size, and then after I'm done using that attributes, basically init would probably do something like malloc, maybe a lot of mallocs. So I have to do the equivalent of free for this attribute, which is this called destroy. So if I run this, so here's the example, what's it called, stack size. So if I just run stack size, it should tell me what the default stack size is on my system. I don't think it probably changed from the last time. So if I run that, I see this number, which is basically just 8 megabytes, I think. So on most Linux systems, that's the default stack size. It's 8 megabytes. If you go over that, then you see a stack overflow and all of that fun stuff. And if you want to play the Java game of like, hey, my program has a stack overflow error, well, if you want to get around that and you think your program doesn't have an infinite loop, you can just increase your stack size, and then hopefully that works. So you can do the Java solution. So that's something you can do, or you can also go ahead and do things like, if I didn't want to call pthread detach, I could set the detached state as part of the attributes and set it as either detached or joinable thread whenever I create it. Again, for this course, we'll just always use the default attributes, and the only attribute we'll use is detach, and we can go ahead and use that pthread detach function. So we can compare the two. So let's see. If I have multiple threads, is this a good example? So if I have multiple threads, actually, let's go for multiple processes first. Multiple. Oh, I don't have that. OK, so let's just assume we're creating multiple threads. We'll see how this works because I'm using a whole bunch of pointers. So go ahead and ask questions. So if in main, I'm going to go ahead and have a for loop from I to 4. So it should go 1, 2, 3, 4. And through each of them, each time through, I create a new thread here, and I pass it the int I. And then afterwards, my main thread, after it creates all of the new threads, it checks for errors. Let's just assume they don't happen. It calls pthread exit, so it doesn't implicitly exit, so that all of the 4 threads I create hopefully also finish. In pthread create, what I have to do here is, if I want to pass a value to a thread, well, I have to do it through a pointer, and I have to make sure that memory survives long enough. So in order to pass it a value, it gets kind of messy. So I have to declare a pointer to an int, malloc some space for it, so that goes to the heap. Again, when I create all my threads here, they'll all have access to that. So they'll all share it. But I'm only going to give one thread that pointer. So here, I dereference that pointer. I set the value through it, and then I create a thread. And then in my thread, I give it the default attributes. I tell it to execute this run function. And the initial value of argument is what I got back from malloc. So if I want to make sure everything works correctly, well, I wrote my program. Again, because of the 3 rules, it just takes a pointer to void. That's like an I don't care. In this case, I know that arg is a pointer to an int. So I can typecast it from a void star to an int star because, again, I know what it's pointing at. Then I can dereference it to get its value. And this int ID here, it's a local variable, so it's on this thread stack. So it is independent for this thread. So I read the value into ID, and then I can go ahead and free that pointer. So now I don't need this heap space anymore. I got that value. It is now in my local variable, and now I can use it. So for each thread, it loops 10 times, and it says thread its ID. So this should happen 4 times, so it should be thread 1, 2, 3, and 4. So it should print off its ID and then I. And then just for fun, I have a uSleep just to add a little bit of a delay just for fun. So in this case, 4 threads execute this. I should see thread 1 and then thread 1, 0, 1, 1, 2, blah, 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 up the way to 9. Thread 2, 0 to 9. Thread 3, 0 to 9. Thread 4, 0 to 9, right? So if I execute this, what's this called? Multiple thread example. We'll see that that indeed is what happens. So here, if I go back up to the beginning, I added that value, that sleep, just so I pretty much always see the same number from all 4 threads, but I don't know what order they're going to be in. So here, for printing off I equal to 0 for all threads, again, I will be independent for each of them. I get thread 1, 2, 4, 3. Then the next time through, I get 1, 2, 3, 4. So the order is not the same. Then I get 1, 3, 2, 4. Then next time I get 1, 4, 3, 2. So I can see that the order is completely different over and over and over again. So any questions about this before I break it? Yeah?
If you remove the uSleep, would you still get the nice 0, 0, 0?
Yeah, so one question is, if I just remove the uSleep, will I get the nice 0, 0, 0 everything? And the answer to that is probably not. Likely, whatever thread gets scheduled first will just dump out everything. So I'll probably see like thread whatever 0 through 9 and then thread whatever 0 through 9. But we can go ahead and test it. Again, this is all up to the scheduler. So yeah, so it's what I guessed. So I see thread 3, 0 through 9. Then I see thread 4, 0 through 9. Then I see thread 1, 0 through 9. Then 2, 0 through 9. Again, up to the scheduler. I just added the uSleep as just a bit of flavor. All right, cool. Any questions about this example? Yeah.
Why doesn't it like have both columns like randomized? It seems like in this example, like when you remove the uSleep, like each thread runs from 0 to 9 randomly, and then previously like the right column was like nice, and the left column was like negative.
The right column was, what do you mean by the right column was nice?
It's like because now it's like thread 1 for like 0 to 9, and then like thread 2.
Yeah, so basically each thread just dumps it out because this loop one's really, really fast. Like printf is pretty fast, so it just, whoever gets picked first just goes through all of them, prints them all out. Or if I have uSleep, it's slow enough that each thread is going to get its turn. So uSleep will essentially like block a thread, so it won't execute, so another thread gets a turn. And that way, if I add that all in there, it's likely, again, not guaranteed, that I'll see everyone prints 0, then everyone prints 1, then everyone prints 2. It just has to do with the scheduler. Again, not guaranteed. There's no reason why, even with the sleep, the kernel could ignore it. It could do whatever. I could see it in any order. All right, any questions about that before I ask my own question and try and ask you what the hell is going on? OK, so one question I like is like, hey, anyone think this whole malloc thing is just kind of a waste of time? So I could be like, screw this malloc. Points, like, all the types can line up. So here in pthread create, I don't need to malloc anything instead of value. I have int, and I can just take a pointer to ID. So I can just give it a pointer. So I'll just give it the address of ID. And then in here, well, I don't need this free or anything like that. So I don't need this free or anything like that. I can just go ahead and read that value of arg. So any guesses what will happen if I do something like that? And this is what makes threads oh so fun. So here, I will give you a hint. Let's compile and run it, although it might not help. Help, I have a bug. Anyone with any guess what the hell is going on here? And as another hint, this thing that's printing thread 2, that's probably not thread 2. That's probably actually thread 1. Yeah?
When you do thread create, that ID number, since it's not in its own memory, the main function runs another run thread, the new value kind of overrides the ID in that address. So when you run it, it actually runs the wrong number.
Yeah, so if you didn't hear that, here is the kind of lay explanation. So now this is where it matters what's on the stack, what's on the heap. So if I write out my main thread here, so main, and I keep track of kind of its variables. Well, it creates a variable called ID. First time through, it's equal to 1. So that makes sense. If I do address of it, I essentially create a pointer to this, right? Everyone got that from first year? So in this case, well, I know my run function from a different thread. So run, let's say run from thread 1. Well, it has its own stack and its own variables and everything like that. So when it runs, it's going to get an argument, and that argument is an address, which is basically a pointer. So it's pointing to the main thread stack, right? It's probably bad if you cross this boundary. So it's pointing to that, and again, we don't know what's going to run next. So this is how it's set up to run. If it was to run, it would just be pointing to that location where the current value is 1. If we pick this thread to run, then the first thing it does is cast that pointer to an int star and dereference it. So if it immediately run, it would get the ID equal to 1, which would be correct, but it doesn't have to run. So what could happen is the main thread continues. So it would go ahead, and this is done through that new thread function. So next time through, it would essentially just delete that, and then we would call that function again. It would create a new ID, likely at the same memory location, but now have that value 2. And now I would be creating run of thread 2. It would have an arg, and it would have an address, and it would be pointing on this computer to the exact same location. So right now, if thread 1 was to get picked for running, well, it would just follow this address, dereference that value, so it would get the ID 2 if it was the next thing to run, right? So this is fun. And this would go on for every single thread. And the reason we got this, horrible value is because, well, eventually the main thread exits and ends, and its stack gets obliterated, and it just takes on random values. So that's where we got that. So those threads executed and read the value at that location after the main thread already died, so I got those random big numbers. So, really important what's on the stack and what's on the heap, right? So if I do it on the heap, well, oops. So when I did it correctly, I created this value all on the heap, which is independent, right? So I created some value on the heap. In this function, I created, I don't know, whatever I called it. I had arg, which was an address, and it pointed to something I malloced, so it pointed to something here, and then I set the value here equal to 2, and whenever I called that run function, right, I didn't give it a value to my stack. Let me delete this. I instead gave it the address to this, which doesn't get changed by anything else, right? So always stay consistent no matter what. Doesn't matter when this actually gets to execute because I only give that malloc pointer to exactly one thread. So I'm guaranteed that no one else is going to mess with that value. It's going to be consistent every single time. Doesn't matter if the main thread exits by then or not, because it lives on the heap. So it lives until you actually call free on it, which again is why that thread had to call free on it originally, because it essentially is the thing that owns that value now. Some languages make that easier than others. Again, C doesn't really care. So any questions about that? Again, when I run this, fun thread mistakes is, oh, cool, now I got 2 different random values and 2 threads got assign the ID 3. So have fun debugging that, huh? So this is why threads is the hardest thing. Conceptually, it's not too much different than processes, but because everything's shared by default and it matters what's shared and what's not, you can quickly get into errors, especially when you don't know what's going to execute next, and you have to argue about every single execution. Makes it really challenging. So any questions about that? Yeah?
I thought each thread has like its independent stack.
Yeah, each thread does have its independent stack.
So when ID2 overridden ID1, which stack was that?
When ID2 overrid ID1, so that ID variable only existed in the main thread stack. And then each thread had an address to the main thread stack, which is not great. So whenever that, so the main thread would be controlling that, but if you're accessing someone else's stack, you're allowed to do that. You're in the same address space, but probably you're always wrong if you do that.
Wouldn't it like add the second ID to the stack rather than overwriting the first one?
So it didn't overwrite it. So in here, in this example, it got an address to the main thread stack, and then here it didn't overwrite it. It just read that value and assigned it to some value on this thread stack. So it essentially, whenever this thread gets executed to run, it reads wherever that memory location was on the main thread stack, whatever it happened to be.
In your drawing, you like crossed out ID equals to 1, so like ID equals to 2.
Yeah, so when I crossed out ID equals to 1 and ID equal to 2, that's like the main thread calling new thread once with ID 1, and then it would create a variable called ID as the argument there. And then it would be assigned the value 1, then it would return, so it would get destroyed. And then we called new thread again with ID equal to 2, and that would create a new ID, value is 2, happens to be at the same memory location as well. Then it exits, ID disappears, call new thread with ID 3, same thing happens. So on and so forth, which is fun. Yeah?
To circumvent that, the release of the heap, couldn't we just pass it directly as like the argument, like instead of passing a pointer to it, and we just like force line text it?
Yeah, so what you can do, which is not recommended, but you can do that is, yeah, this is just pass by value. So instead of an address, I can just shove an int in there and then typecast it back so it will be passed by value like any other C value. So if I just do this, and instead of a pointer, I just force an int. Again, my compiler is going to initially complain at me, probably, that like, hey, jerk, this needs a void. And then, of course, I could be like, yeah, of course, an int's a void star. And then it kind of complains at me too, but it'll still compile. It just says warning. Who cares? Warnings are fine, right? So I can do this. The problem is it's not super portable because an int needs to fit in a pointer. On this case, on this machine, it does. An int's 4 and a pointer is 8, so it would fit. But you'll also get into issues where this will work if it's little endian and will not work if it's big endian. Also needs to fit. Also, you're not guaranteed the size of a pointer. You could be using a microprocessor or something that's like a 16-bit address, in which case you're screwed. So should just use pointers if you want to make sure it works. Otherwise, you're going to get into weird architecture difference where, yeah, sure, it might work for a while on your machine, but you port it to a different one, and then you get a whole bunch of bug reports of people saying your program's broken. What the hell? Yeah?
Can you explain again why we get like strange addresses when we don't malloc versus like why it just runs 1, 2, 3, 4 or what you do?
So the strange values when we didn't malloc came from, like, basically each thread had a pointer to some value in the main stack, right? For this, when we didn't have malloc. And when we got the real weird values, it's because before the thread's executed and like this basically just reads the value at that address, which is on the main thread stack, the main thread was already dead. So if the main thread was already dead, the value it just has is just undefined. So that's why we got random numbers, because in that scenario, the other thread started executing after the main thread was dead. So it didn't have any local variables because it didn't exist anymore. So we just read garbage values. Does that make sense? Yeah, it's, again, kind of messy. You want to avoid those cases at all costs because it means your program has a bug with it. All right, any other last minute questions before we take our fun break? Oh, the doorbell's ringing, cool. All right, so threads enable concurrency. We explored threads, related them to something we already know, processes. Basically lighter weight, share memory by default, and each process can have multiple threads. Again, how I like to think of them is initially processes just have a single thread at the start, just called the main thread, and we can add more to them. So let us take our 10-minute break. Alrighty, that is it for our break. So, oh, also for the midterm, study tip for the midterm. You have not completed lab 3, correct? It's due after the midterm. Your exam is, wow, Wednesday, that's fun. So, the questions where you have to like go through and translate things and all that, Lab 3 is supposed to help you with that. You have not done Lab 3, so those questions I probably wouldn't worry about too much of like actually translating it because you're not done Lab 3 yet. So you should know conceptually about multi-level page tables and how they work. I will definitely ask you a question about that, but I will probably not ask you a mechanical question about that because you've not completed Lab 3 yet. So that is a little hint for your test 1. But again, good to know how to do it. Your time was not wasted. I can still ask you about multi-level page tables, but going into like super nitty-gritty details, I don't really need to do. Again, that'll probably be covered on test 2 because, well, year 1 is short. You only have 50 or 45 minutes. All right, so with that out of the way, let's talk about more threading stuff. So this is also kind of to get you prepared for lab 4. So in lab 4, you will be creating your own threading library. So that will be fun. It's actually fun. I also simplified it, so I'll have a lecture to help you get started on it as well. So we'll do that next Monday, the one not on reading week, the one after that. So you'll be implementing it. It will be fun. I cut it down. It used to be like an 80-hour lab or something like that. It is cut down to be much more reasonable, and again, I will help you get started on it. So, before we do that, we have to talk about multi-threading models and how we would implement threads. So, there's 2 main ways to implement them. We can do either something called user threads or kernel threads, which implies kind of where you would implement them either in user mode or kernel mode. So, user threads are completely in user space, so the kernel doesn't treat your threads in your process any differently. From the point of view of the kernel, your process is running in a single actual thread, and then you are just bouncing that thread between different, well, internal user threads. So in that case, you're just doing concurrency. So kernel threads, on the contrary, are implemented in kernel space, so the kernel manages everything for you, and it can also treat threads specially because guess what? The kernel knows about them. So it could schedule them to run in parallel or do different things based off whether or not they block or not, which we will get into. So thread support requires some type of thread table, so similar to a process table we saw previously. Again, could be in user space or kernel space depending on the implementation. For user threads, there also needs to be a runtime system to determine scheduling, so you're going to have to do some scheduling for your lab 4, but you're going to do first come, first serve. It's not going to be that bad. So don't worry about that. And in both models, each process can contain multiple threads, so that still exists. So the nice thing about using user threads is to create them, I avoid system calls, or I could just let a single thread block everything. So that is basically our trade-off. So for pure user level threads, again with no kernel support, they're going to be very fast to create and destroy because I don't have to do a system call. I don't have to let the kernel do any context switches or anything like that. I would be the one switching between threads. But the major drawback is because the kernel doesn't know you have multiple threads running, if one thread blocks, so if one thread calls read or something like that that's waiting for some slow resource to come in, then that entire process gets blocked. The kernel can't distinguish that, hey, maybe another thread could actually run while this thread is waiting for some result to come in. So for kernel level threads, they're going to be a bit slower to create. That creation will involve system calls, but the nice thing about that is if one thread blocks, so if it's doing a read system call, and there's another thread that could be executed, well, then the kernel can just simply schedule the other thread to run. So even if you have a single CPU core, it is also beneficial to have kernel threads instead of user threads. And there, of course, is some trade-offs between them, and we will get into them, but those are the major trade-offs there. So all of the threading libraries you use technically do run in user mode, and that thread library maps threads to kernel threads. So for different implementations, you can have many to one, where many to one, where's my cursor? Where many to one means threads are completely implemented in user space. So that means every single user thread is mapped to a single kernel thread. So the kernel only sees one process or one stream of execution. The other one, which is basically the idea of kernel threads, is one-to-one. So one user thread maps directly to one kernel thread, and the kernel basically handles everything, including scheduling and all of that. So in lab 4, you'll be doing pure user space, which is many to one. They'll all be in user space, while the pthread library is an example of one-to-one. So one pthread is basically one kernel thread. And then there's also the crazy scheme of many-to-many, where many user threads may map to many kernel threads, and it depends. Usually you try and do the best of both worlds here, where you have lots and lots and lots of user threads mapped to one kernel thread, but you also have multiple kernel threads. So you could make it so that you only have as many kernel threads as things that could actually run in parallel on your machine, and then just kind of map a whole bunch of user threads, thousands or tens of thousands of them, onto one of those, I don't know, let's say 8 kernel threads. So again, like I said, many to one is that pure user space implementation. It's fast and portable, doesn't depend on the system. It's just a library. You've been writing libraries so far in the labs. Drawbacks, again, are that if one thread blocks, all of the threads block. And of course, we cannot execute threads in parallel. We can only do concurrency, which is fine if you're doing a whole bunch of slow operations. For example, like Node and all the async libraries basically just use user threads, and they just use some kernel functionality that if they're doing some slow operation, they can actually switch to a different user thread while the kernel actually does that operation in the background. So we can trade off between them like that. So in this case, the kernel just schedules the process to run. It's up to the library to decide which actual user thread gets to run. One-to-one, again, just uses the kernel space thread implementation. It's basically pthread. The pthread library is basically just a thin wrapper around the system calls to make it easier to use. This way, I can actually have the full parallelism of my machine. The kernel can schedule multiple threads to happen simultaneously, aka in parallel. Of course, it could do it concurrently as well. But it does need that slower system call interface, and you lose some control because, of course, you don't have control over the scheduling. The kernel gets to decide that. So typically, this is the implementation you actually use, and we assume this for Linux pthreads. Many-to-many is a hybrid approach. Again, the idea is there's more user-level threads than the expensive kernel-level threads. Again, idea might be to cap the number of kernel threads to the number I could actually run in parallel. That way I get the most out. I try and get the best of both worlds. I get the most out of multiple CPU cores and reduce the number of system calls. But however, this is always bad. It leads to a very complicated thread library that has very bad performance issues. And this trend seems to come and go. Currently in the Java world, it is coming back. And they have named it Java Virtual Threads. But they use this approach. But it's typically very, very, very hard to debug, especially if you're having performance issues. So depending on your mapping luck, you may block a whole bunch of other threads. So let's consider, I don't know, I have 4 CPU cores and I have 100 user threads. So I map 25 user threads to one kernel thread for this Java Virtual Threads thing. Well, let's say only 4 of those threads do something that blocks. Well, I could get lucky and have one of each of those 25 threads in that kind of group of user threads mapping to the same kernel thread. They could all be in different groups, and that way, actually that's the worst case. So that way, if they're all in different groups and they all block, then guess what? All of those kernel threads are now blocked, and now your application will not make any progress, even though you might have 96 other threads that could make process. And that will just depend on your luck. Or you could get lucky, and those 4 threads that actually block are all scheduled or are all mapped to the same kernel thread, in which case the 3 other kernel threads could go ahead and make progress while that one thread is blocked. But again, you will typically not have control over this, and sometimes you run your program, it's slow, sometimes you run your program, it's fast, and you're not going to debug it. Also, it's very hard for that threading library to get it right, and again, like with most things in computing, ideas come and go, come and go, come and go, and the general idea is that this is a very poor idea, but again, just as a word of warning, it's coming back in Java Virtual Thread, so probably avoid those. So, threads also complicate the kernel. So, we have threads, we also have fork. So how should fork work with a process with multiple threads? So, different ideas we could have if I have 8 threads in my process and I fork it. Well, if it's an exact clone, then that new process should also have 8 threads. They could all be in different states, so maybe they're just cloning that new process in whatever state they are. That would get out of hand very quickly. One, it would be hard to argue about what state they are. 2 is, well, this would get out of hand. Remember our good old friend, the fork bomb? Imagine we could do a fork bomb, but we also create threads at the same time too. So we can make our fork bomb even more effective if, well, we fork and we also fork with multiple threads. So the rule Linux uses for when we fork in a process with multiple threads is Linux will only create a new process that is a copy of the thread that called fork. So it will just create a new process with a single thread in it, and the thread that is running is going to be a copy of the thread that called fork. And in that new process, if it hits pthread exit, that means, well, now it hits pthread exit. This is the only thread in that process now. So it's going to terminate that process. By default, it will just set that exit status to 0, and that process will terminate. If you want to control what happens to the other threads at a fork, there's this pthread at fork call. I will not cover it in this course, but that is how you can control what other threads do whenever one thread calls fork to try and make memory consistent. But basically, if you try and use that, you are probably making things very complicated for yourself, and we will not be covering it in this course, but it is an option. All right, signals. Signals are also fun. So right now, if our process gets set a signal, we can handle it. Well, if I have a process with 8 threads and I send a signal to it, what happens? Should every single thread receive a signal? Well, the rule for Linux is it won't just send a signal to every single thread. It will just pick one at random to handle the signal. So this makes your life even more complicated because any thread could get interrupted at any time. It's not guaranteed to be the main thread because, well, when you get sent a signal, it's not guaranteed that your main thread even still exists. So the Linux thing is just, it's guaranteed that it will send it to exactly one thread. Which thread? I don't know. So that makes handling signals with threads even more fun. So also, instead of many to many, instead of using like that hybrid approach, you can use something called a thread pool. So the goal of this is to kind of do that many to many thread mapping to avoid creation costs. So a thread pool will create a certain number of threads and a queue of tasks, basically as many threads as there are CPUs in the system. And then I just keep those threads active and keep on reusing them and keep giving them little tasks to do. So as a request come in, I can wake up one of my threads, give them some work to do, and then whenever they're done, I can put them back to sleep. And then that way, I just have one set of creation costs, and then I reuse them all the time. So I don't know, you can find an implementation for thread pools in Python or C or whatever. So if you get into performance programming and you really want to avoid that startup cost, you can use something called a thread pool. Again, aside from mentioning it, we will not really cover it in this course, but it is a good thing to know. So for lab 4, you'll be implementing many-to-one. So you'll be creating your own thread. So this is going to be your state diagram for the lifetime of your threads, just like a lifetime for a process, same idea. And in that lab, everything will be prefixed by what, because, I don't know, I seem to like 3-letter acronyms. So what stands for wacky user threads? I don't know, I'm easy to entertain. Putting what in front of everything, I don't know, made me chuckle a little bit, so whatever, I did it. You're not the boss of me. So in order to create a thread, well, to transition from this created to waiting state or ready state, there's a function called whatCreate. Basically looks like pthread create. It's just simplified a bit, so I don't have you pass arguments or anything like that. So the function to run takes no arguments, returns no arguments. Then we have this waiting state, or actually it might return an int. Then we have this ready or waiting state, and you'll be picking what goes in running state just based off first come, first serve. And like for processes, we can have true multitasking or cooperative multitasking. For your lab, you'll be doing cooperative threads. So they will run until they actually terminate by calling what exit, or they relinquish the CPU by calling what yield. What yield will basically just put them at the back of the queue and let another thread go ahead and run. And then you are also going to implement what join, so you're going to be able to join on another thread. That will transition it to a blocking state because it's waiting for another thread to terminate. And then when the other thread terminates, then it would get added back to the queue and go in this ready state. So we'll come back to this when we talk about lab 4, but again, and all these transitions also exist for the pthread library. Just the only difference with the pthread library is that it's true multitasking, so transitioning from ready to running is determined by the kernel scheduler and not yours. So again, your scheduler can just be round robin. That's what you'll be doing for lab 4. You'll just create a queue, a list. I'll show you how to do that instead of implementing your own. It'll be easy because you'll run the thread at the front. When it yields, you throw it to the back. It'll be a doubly linked list. I will show you how to use it. Again, don't have to implement your own. You'll also have to do the context switch, which will save the registers. I will show you a function that will do most of the heavy lifting for you, and we will be doing context switching in an example lecture again in a Monday, well, in 2 weeks from now. So these are cooperative threads, so they have to be nice. You could extend this to preemptive threads where you just essentially force them to yield, but we will not be doing that. So our next complication is going to get into what makes programming threads fun. So let's get into it here. So, whoops. So let's see this little program. So at the top here, I have defined numthreads8, then static int counter. So this is a global variable called counter. I initialize to 0. Then in the main function, what I do here, I have an array of, well, an array I called thread. Maybe I should have called it threads of type pthread underscore type. And I have, it's of size numthread. So it's of size 8. Then here, I have a little micro optimization. I don't know why. I share I between my loops. So I have int I here. Then I go from I equals to 0 to numthreads. So this should run 8 times, right? And then what it does is call pthread create. It will initialize the value in the array. I give it the default attributes, tell it to run the run function, give it no arguments. So I set off, I create 8 threads. I don't know what order they're going to execute in. And then my main thread is going to join on all 8 threads. So my main thread is only going to continue here after all of those 8 threads are done. So it joins on all of them, so it waits till they all terminate, cleans them all up, and then it prints the value of the counter. So let's see what all 8 threads are doing. So all 8 threads, okay, that just looks ugly. I'm just going to move it because it bothers me. So all 8 threads go iterate 10,000 times, and they all just do plus plus counter. All right, so if I run this program, anyone want to guess what the final value that I'm going to print off for counter is going to be? So I have 8 threads, and they all increment counter once, 10,000 times. Anyone need their calculator? Yeah?
Sure, it's 80,000.
80,000, right? Everyone agree? 8 threads incrementing the same value 10,000 times, 8 times 10,000, 80,000. So this is also a good way to calculate your marks too, right? I can just add it up. I'll add it up one at a time. So let's see what we get here. So pthread data. Uh-oh. The course average went down. So if I run it again, oh, no bugs. My program works perfectly. Run it again. 72, oh, slightly better. Ooh, that's real bad. 59. Run it again. 59. Ooh, that's not good. 70,000 on the dot. 71,000. 70,000, 70,000, 68. Oh, 70, that was almost right. Good enough. 80,000, twice in a row, no bugs. So, anyone have any idea what the hell is going on here? Yeah. Yeah, so here pays off to pay attention in your architecture course. So plus plus counter looks deceptively simple. So up here, let's just argue about. So I have a global variable called counter, right? Well, it's in virtual memory. I'm using threads. Everyone can access it, right? So I have this variable called counter. Initially, it's equal to 0. We now know that counter exists somewhere in memory, right? So this is counter. If I was to write a pointer to counter, it would be pointing to that. That virtual address is something the compiler picks for me, whatever. So everyone good with that so far? Just a global variable. So I will argue about, let's just break down what happens in thread 1. So if I have plus plus counter, that is a deceptively simple instruction. So what plus plus counter actually does, if you break it down architecturally, is it will essentially just use a random register, let's say RA for argument's sake, and, well, what plus plus counters do is first it will read the value of that counter from whatever it is in memory. So it will essentially just dereference pcounter, which is like a load, some load instruction, right? Then it will increment its register, and then it will essentially do a write. So it will write the value of that register to overwrite whatever, just do a memory write here. So Might call it a write, might call it a store, depending on, I don't know, how architectural you are. So plus plus counter actually does those 3 steps. So thread 2, well, thread 2, it could be doing that as well. It's also doing plus plus counter. What the hell are all these buttons? I just want copy. Go what? Paste. So thread 2 is also doing the same thing. So if this happens, well, if thread 1 executes completely, it's going to load the current value of counter, which is 0, right? Then it's going to increment it in its register, which is 1. Then it's going to write the value out and update the counter from a 0 to a 1 like this. Then thread 2 is going to come along, load. So it would load the current value of counter, which is 1, increment it in its register, make it a 2, then store the value 2. So that's what would happen in the happy case or the good case. But now, because we have threads, well, easiest way to argue about threads is just argue about them concurrently. So all of those instructions will happen in order for the thread, but I have no idea what the order is going to be between threads. So as a teaser for the next lectures coming up, what could happen is my order goes like this. Thread 1 executes this load. Then thread 2, it switches to thread 2. Again, just arguing about concurrency, so on the same CPU core. So we context switch over to thread 2. It loads the counter value, and then it increments it, its register. Then we switch to thread 1, it increments its register, and then thread 1 stores, and then thread 2 stores. So don't worry about writing this for now. Again, we'll be arguing about this ad nauseum in the next lectures. But in this case, what happens is if thread 1 executes first, it loads the current value of counter, which is 0. So it would load 0, and that value of 0 gets assigned to its register. We switch to thread 2, so it would load the value of counter, which is now still 0. So it loads a 0, then it registers, then it increments its value in its register. So the value of RA changes to 1. Then we switch back to thread 1, and again, remember, each thread has its own set of independent registers. So its value in its register is still 0. So when it increments from 0 to 1. And then at this point, it would store the value in its register to that memory location. So it would store a 1. So that counter would get, 0 would get replaced by 1. Then we would switch back over to thread 2 here. And then it would also write the value 1 over 1. So it would just overwrite that same value. So we get some of a disagreement. So essentially, if this happens, we lost an increment, right? So that's why when we run our program, we always get different numbers. The number we got is basically how unlucky we were, how many times we got interrupted doing that, or we got context switched between them, and we actually got unlucky and missed a count. So that's why it is not consistent. Sometimes we get omega lucky, and it's fine. We don't miss anything. That's because the operation's really fast, but c'est la vie. All right, any questions about that? All right, without knowing something complicated, is there a way I can change this program such that it will always print 80,000? Yeah?
Join immediately after create?
Yeah, join immediately after create. So join immediately after create. Everyone agree with that? Will I always get 80,000? Well, we can try it. 80,000, 80,000, 80,000, 80,000, 80,000. So now it works. But if we were using threads for increasing performance and wanting things to run in parallel, we have fallen into, one of our first traps when you first learn threads is that just adding them will speed up things. Well, in this case, we actually slow down things. So if we create a thread and then join it, it means only one thing's running at a time, right? So the main thread's creating a thread, then joining it immediately. So the only thing that can run is that thread. So basically, I'm just making a serial program. So one thread increments 10,000 times. It's the only thread existing. It would increase counter until it gets to 10,000. Then another thread would get created, run, increment to 20,000. Then we do one after the other, after the other, after the other. It'll be consistent, but it's basically just using a single thread with more steps. Any other idea for how I could do this in a way that's safer? I'll always get 80,000, and I can do it in such a way that even if I do the join right after, it still always works. Yeah?
You could increment 8 separate counters?
8 separate counters?
Add them up again.
Yeah, so I could add up 8 separate counters and add them up all at the end. So one way I could do that is, well, I could create an array and then make sure that each thread accesses a single element of that array, have it increment it, and then have the main thread do it all at the end. Or I could leverage the fact that it returns a pointer to something, and I can go ahead and in here, instead of counter, again, kind of a contrived example because, I mean, if I'm just incrementing something, it's really fast. But if I wanted to do this in a safe way, I could do something like, hey, I could create a local counter. So I could create a local counter, initialize it to 0, and instead of incrementing the global variable counter, I could do something like this and just increment local counter. And then at the end, I could go ahead and return that value to main. In this case, I have to give it the address of pointer, so I'm going to have to do that malloc thing again, where, OK, now I have to, int, let's call it A because whatever, we're running low on time. I could do something like malloc. I'll save myself writing size of int. We need standard. Whoops. Uh-oh. What'd I do? All right, so we could use the standard library, so we get malloc. And then we could write the value of local counter to it. And then just return A. So that's how we could return our value back to main. And in main, well, we could have the main thread go ahead and just add the result of every thread's final output to the actual counter. So we could set up int star, I don't know, whatever they returned, initialize it to null. And then here, we actually use the thread's return value, so we can give it the address of ret. We're going to get a compiler warning because, of course, we are at C. It will probably demand a void star star. So we can see our types kind of line up. It got void star star, or we gave it int star star, but I expected void star star. Again, that's just the rules of C's type system, so I can shut it up. I can typecast it to void star star. That's fine. Then in here, I can go ahead, dereference it, so that will get me the local counter returned from the thread. So I can add it to counter. And then I can go ahead and free whatever I got, make sure I clean up memory, make sure Valgrind's all happy at me. So this is another way I could do it, where if I compile and run that, I'll go ahead, I get 80,000 every single time now. But I did it in a more roundabout way. But this is still safe, right? I let every thread, I made sure every thread only incremented its local variable. So it's independent. I know there's no trouble with it. Then I give it all back to the main thread, and the main thread is the only thing that adds to that counter variable. Nothing wrong with that. In fact, if you invented this, I don't know, 20-ish years ago, this is some idea at Google called basically map reduce. So You do some operation independently in each thread, and then once each thread is done what it's supposed to do, hopefully in parallel, you kind of reduce all the results to get you the final result you wanted. So this is a good thing to do. We'll see other ways to fix this because maybe some problems don't actually go to this. So I'll show you other ways to fix that. That will be our content after reading week. So that will be fun. So we can wrap it up in the last minute we have. So both processes and kernel threads enable parallelization. Each process can have multiple kernel threads. Most implementations use 1-to-1. So one user thread is one kernel thread. That's what P threads are. The operating system has to manage what happens during a fork or signals. For Linux, when you fork, new process gets created, only one thread, copy of whoever called fork. Signal gets sent to a random thread. But now we have synchronization issues, and that's what we have to look forward to fixing once we come back from our break. So just remember, pulling for you, we're all in this together, and good luck on the midterm, and good luck waking up and no snow.